Hello all, welcome to Cyber Physical Systems Design, Modeling and Simulation. Before we go into today's video lecture, I would like to have a quick recap of whatever we have done from class 1 till now. So we just initially saw what is a cyber physical system and how it enhances in connecting the physical world with the digital world. Then we saw the attributes of CPS, important attribute being real-time interaction, adaptive intelligence, interconnected complexity. That is the way it connects the physical components, the computational elements, and the communication networks. Then we saw the various application domains of CPS. CPS can be in agriculture, transport, healthcare, and manufacturing. As an overview, a cyber physical system is a computing system that integrates physical processes with computational algorithms and networked sensors to monitor, control the physical process in real time. So basically it bridges the real world and the virtual world. Here the physical or the real world is nothing but sensors, actuators, antennas, and the virtual world is nothing but protocols, communication, security, encryption, algorithms, and so on. So this is how the cyber physical system networks everything, to make sure we will be able to monitor, control the physical process in real time. Now with the features of CPS, real-time computation, concurrency, robustness and reliability, network connectivity, and above all, reactive computation. I've already dealt about this in the class. What is reactive computation? How is responsive different from reactive? Now this set of features of CPS can be found almost everywhere, whether in decision making or self-management or dynamic reconfiguration, or while even intelligent data acquisition systems, environmental monitoring. You take any example for that matter. If it is made of CPS, definitely you will have all these components involved in that. Now this is the generic framework or a platform of a CPS. When I say generic, it's very basic. At least a CPS will have something like this. So it will have two platforms, each having its own set of sensors, computations, and actuators, networked by a network fabric. When we say network fabric, it is nothing but communication protocols connecting the two platforms and translating the communication if needed. Now, an important step in CPS design is verification and validation. I've already told you the difference between verification and validation. It's a very key process. It must handle the physical process individually and the computational, individually the physical process and the computational process. Must take into account the mutual influence of the physical and computational domains. In the sense, sometimes the physical domain lays restriction on the computational domain. Sometimes the computational complexity and the resource requirement will lay a restriction on the physical domain. So verification and validation steps involved in CPS must take into account both these. How? By using some standards. Now we saw the design principles and validation methods of CPS, system integration, architectural considerations, and attributes. System integration, it has to make sure smooth integration of cyber and physical world. The robust communication interfaces must be there. Interoperability between heterogeneous system. Modular and flexible design. Again, I have explained this in class. A single CPS will not be one single component. It will be multiple components stitched together. So it's in a modular form. So your system integration should have the ability to accept modular connections, and it should be flexible in design. Now, as far as architectural consideration is concerned, the infrastructure should be scalable. We all know that. Real-time processing capabilities, adaptive and reconfigurable designs, distributed system architecture. Obviously, when it is modular, it's distributed. Key attributes of CPS we came across: reliability, energy optimization, fault tolerance, security and privacy, performance efficiency. Now, as far as validation methodology is concerned, there are two processes. We saw that one is verification and one is validation. We also saw the difference between verification and validation. Please recollect the explanations given by me in your class. So when it comes to verification and design methodology, we have model-based, simulation-driven, and experimentation-based, designing and validation of CPS systems. And when it comes to validation of these verified designs, it can be done as hardware in loop, or shortly called as HIL, software in loop, shortly called as SIL, comprehensive edge case. I also gave you the definition of what is comprehensive, what is edge case, what is software in loop, and hardware in loop. Now, in development, verification, and validation, there are several ways, three ways basically, mainly model based, simulation driven, and experimentation. And initially, we saw model based, what are its key characteristics. Then we saw about state space exploration, represented as state transition system. I told you what is a state, what is a transition, what is an initial state, final state, all these definitions were given. And I also dealt with, verification. What do you mean by verification? A model based state space exploration. So finally, we end up with state space model. I told you states machines are, different types. One is called finite state machine, FSM, NFA, non-deterministic finite automation, hierarchical state machine, HSM, Mealy and Moore. I give you definitions of each of this. If you want, recollect your notes, or you can go to Google what it is, and then find out what they are. Now, there are several tools that you can use for state machine modeling, such as UML state diagrams, SCXML state charts, formal specification languages, programming language, state machine libraries, like Simulink is one good example, LabVIEW is another example. Now, I gave you some of the examples of state space model which you can try on your own, like traffic light system, door lock system, elevator system, and washing machine. As an example, in class, we did a very simple state space modeling of washing machine. Now, that is a very, very simple basic system overlooking many of the features what a washing machine nowadays has. For example, state diagram, of a washing machine. If you look at these are the several cycles of the washing machine. It goes through a full cycle and then comes to a halt. Now, this system can further be made complex by adding, power check, in the sense, for example, when you say start, if the power is there, it will start. If not, it will still be in the same idle state. So power is the trigger there. So you can add complexity by having a power check trigger. And memory. What do you mean by memory? For example, let us assume that the machine is in a halfway of spinning cycle, and suddenly the power goes off. What will happen? When the power comes back, it again resumes from spinning. It doesn't again go back to the initial state or get reset to zero. So that is called memory. This doesn't have a memory. You can have a memory at each cycle, each of the state. Then again, this is under the assumption that once you start, it will fill water, wash, rinse, spin, and then stop. What if, I just want the clothes to be washed, not rinsed or spinned? Or again, if I want the clothes to be just rinsed and not washed or spin, or if I want the clothes only to be spun and not washed or rinsed. So these are individual cycles which I may want to perform. That is not considered here, but you can add the complexity by doing so. Similarly, water level is based on the load level. If the load is too much, it has to be full water. If the load is light, even a quarter of a tub of water is good enough for it. And then if I want to directly go for a wash or soak and then wash for a longer time, like heavily soiled clothes. So these are the complexities that can be added to this state diagram. This is a very simple state diagram where you say from the initial state it will be idle. When you start, it fills water. When the water is full, this is the trigger. It triggers from filling water state to washing, and then when the wash is complete, it goes to rinsing, and when the rinse is complete, it goes to spinning. When the spinning is complete, it goes to a complete state. From there, it gets reset to the idle or the initial state. Now here, if you see, when it is in the idle state, start triggers the machine from idle state to filling water, and when it is in the filling water, the water full indicator triggers it from filling water to washing. So the ones you see near the arrow marks are nothing but the trigger signals, and these are the states, and these arrow marks tell you the flow of the states. So what will be the next state in the transition? So this is a very simple state diagram, which can, as I told you, can be extended by adding more complexity to such a model so that you can cover all aspects of the washing machine. Now, the next set of modeling technique is called simulation-driven approach. Uh, Generally, if you see, CPS rely heavily on simulation to ensure reliability, optimized performance, and verifying functionality before going into implementation. Now, simulation based approach is like, or simulation based development is like something that bridges the gap between theoretical design and practical implementation. So now, before we get into the simulation based design, we need to define system requirement. That is very, very important. We need to define system requirement. And when I say system requirement, what are the system requirement? Objectives, input, outputs, and constraints. Now, when I say objective, what do I mean by objective is for what purpose the CPS has been developed. Is it for solving a particular problem, or is it to identify a particular problem in a system? So what kind of objective is being taken in hand to develop the CPS, or in other words, what exactly is the problem statement for which the CPS is being developed? So that's the objective. So once the objective is defined for the CPS based system, then we need to define the inputs. That is, what are the signals that are going to be obtained from the sensors? What are the signals that are going to be user defined? All those things has to be clearly stated. And similarly, output. When I say output, it means what is the action that needs to be performed by the CPS when such inputs come in, or what should be the reactive mechanism of the system, of the CPS system, when these inputs occur. And the next thing that you need to define are the constraints. Constraints are nothing but constraints can come in various forms. It can be a physical constraint, it can be a computational constraint, or it could be a time driven or time oriented constraint. It can be anything. So all these 4 steps are very important in a simulation driven approach. As we go down the presentation, we'll see why these 4 are very, very important when it comes to simulation driven approach. Now, how do you do a simulation driven approach? There are various tools available for you, such as Simulink and several Python libraries such as SymPy, PyBullet. Or if you say, hey, these are all already defined, they are restricted, I want to customize my own simulation, then there is something called ROS. It's called real-time operating system. It is for custom modeling. So in this custom modeling, you can define your tasks, you can define your threads, you can define how the task can communicate with one another, what kind of scheduling can be done, which has more priority, where the interrupts will be generated, where the interrupts will not be generated, which are the interrupts that are maskable, non-maskable. All these things can be customizedly defined by you in the ROS custom modeling. Now, having defined the system requirements and using one of these tools, we go for simulation-driven approach. This is nothing but a flow-based illustration of simulation-driven modeling of a CPS. So, as I told you before, you first talk about requirements and specifications. This is where we define our objective. Objective is nothing but the functional requirement. Then these are nothing but the input output requirements. So if this is the input, this is the this is the kind of performance is needed, or if this is the input, this is the kind of reaction or responsives is needed from the system, and how quickly it should respond or react, and when it does so, what are the safety requirements. So these are the requirements and specification step which needs to be first developed. Once this is defined, then we go for software based system modeling. So we have physical models, we have control models, we have network models, and we have environment models. That is, every component in a CPS, okay, will always be a combination of physical, control, network, and environment. So how are you going to use simulation to define these models individually, so then they can network with each other, and then simulate an artificial environment in which these CPS will work. Now, once this is done, then the actual simulation environment will take place. We can co-simulate, we can have real-time simulation, or we can have hardware in loop. This we'll talk about it later, what this hardware in loop, how this comes into the simulation based design of CPS. So all these things are done, and once the simulation is done, the result goes for analysis and verification. Like we have already defined our functional performance and safety. So at the analysis and verification based on the simulation results, it is analyzed whether the performance is met, whether the safety is met, whether the validation is being properly formed, and depending upon the results of these verification, the system is fine-tuned. And then once it meets the requirements, finally it is implemented. So this is how simulation-driven modeling of a CPS system is going to take place. So again, to summarize, requirements and specification are defined first, where we define functional, performance, and safety. Once that is done, we categorize them into physical, control, network, and environment. Based on that, we decide how we model each of this in the simulation environment. And then once it goes to the simulation environment, we can either use a co-simulation engine or a real-time simulator or hardware in loop to simulate the environment or your design. Then it goes for analysis and verification, where the already defined specifications are checked whether they are met or not. If not met, there is a refinement in system modeling happens, and then again it goes to the simulation. So this is like a loop. This is iteratively going in a loop. This you see, this iteratively goes in a loop till you get a perfect system where it meets all the requirements. And once it meets the requirement, it goes into system implementation. That is, we take it to the hardware level implementation. Now, in simulation driven approach, as I told you, we co-simulate physical and computational models. We do scenario testing, and when we do scenario testing, we test it for all possible scenarios. As I explained in the previous slide, it's an iterative optimization. That is, the simulation models are done, then the simulation is done, then the performance analysis is checked. If doesn't meet the requirements, fine tune, simulate, check, fine tune, simulate, check. So it's an iterative optimization method. And then once the requirements are met within the tolerance level, the software models are being the optimized software in CPS is now taken to hardware for implementation. Now, what are the pros and cons of software driven simulation modeling of CPS system? The pros are reduced development time. In the sense, basically the software driven approach helps you to accelerate prototyping and testing. To give you an example, if I give you a breadboard and a set of components and ask you to construct the circuit and then test for its functionality, yes, you can do that. Suppose a resistor goes off or component goes off or something doesn't work. Imagine the kind of effort you need to put to debug, test, and then replace the components and then work on it again. The breadboard could have loose connections, the components could have loose connections, the wire could have lost connectivity in between. There are so many things that you need to take care of when you actually put it into hardware. Whereas in simulation, it's quite easy peasy. You can easily take it, rewire it. The components doesn't go away that easily. So in a way, it gives you an idea of whether your concept is going to work or not. So that is what we mean by reduced development time. Then improved reliability. What we mean by improved reliability is it identifies and resolves issues before even deployment. In the sense, nowadays tools are so sophisticated that not only it tells you how to design it in the simulation, even when it gives you an error, it tells you exactly where the error is and what the error is, so that it's easy for you to go and rectify that error. Next is enhanced stability. When we say enhanced stability, your software-based or simulation-driven modeling can easily adapt, to a larger systems easily. So that is what we mean by that. Then risk reduction. It is very closely associated to that improved reliability concept of in hardware. Suddenly you burn a board, you burn a chip. it is going to be a costly affair and people may not trust you. But whereas in software it doesn't matter. So in that way it's it contributes to risk reduction. Then cost effective. You don't have to buy a single component assuming if everything is available in the simulation tool. All you have to do is drag and drop. It costs you nothing to buy the components. Now these are the pros. And when it comes to cons, if you see modeling complexity, what do we mean by modeling complexity? Let me just go back for that washing machine based thing. Now if you look at this is very simple, either to simulate or write a code and then make it work. This is very, very simple. But does a real washing machine look like this by any chance? No. As I told you, the real washing machine is much more complex, where all these information needs to be added to this kind of a simple state diagram. When you add all these things to the state diagram, just try it out and see how complex the state diagram becomes. The moment the state diagram becomes complex, separating out into physical, network, computational model is going to be difficult. And once you are able to assume that you are able to classify them separately properly, simulating them is going to be very, very difficult. So that is what we mean by modeling complexity. As your system model develops into a more and more real time, the simulation modeling becomes complex. Now the second point is validation challenges. What do we mean by validation challenges? Validation challenges are nothing but simulation has some implicit assumptions, okay, and with that only we make the simulation. Whereas on the contrary, real-time scenarios need not meet the implicit assumptions that we have in the simulation. So while we validate a simulated environment for real-time conditions, validation could be challenging. And risk reduction. Enhanced stability is a typo, please ignore that. Risk reduction, again, though we say risk reduction is a pro, it is also a con, in the sense when you simulate, I told you no way you can burn a RPI, no way you can burn a resistor or an LED. So in that case, you don't care about any precautionary methods of putting load resistors or any kind of connectivity or fan in fan out capabilities of the hardware. But whereas in real time, all those things matters. So though that advantage is there, that is also a disadvantage in simulation driven. Then cost is also a con. Now simulation driven is cost effective in the sense it doesn't it doesn't require you to go buy components which is going to cost you. That is agreed. But let's say you need a particular tool to simulate a particular model, and that tool is a proprietary software. You need to buy license for it, like say MATLAB, which is going to cost multiple lakhs, like 50 lakhs, 60 lakhs. Then that's a con. Hardware doesn't cost you that much. Even if you build an entire prototype, with the TRL 6 level ready, it may cost you at max like 1.5 lakhs, or worst case 5 lakhs, not beyond that. But whereas the tool that you may need, if it is not available, procuring a license and then making it proprietary of yours is going to be a very costly affair. So pros: reduce development time, improve reliability, and cost effective in terms of component purchase. Now this enhanced stability, risk reduction, and cost effective, they are both in pro as well as con, especially risk reduction and cost. With this, we have come to the end of the hardware based simulation, which is nothing but state modeling and simulation driven modeling of cyber physical system. Having said all these things, even though cyber physical system, when they are simulation driven modeled, has a lot of advantages, but one thing what we need to remember is whenever you are planning to go for a simulation driven CPS modeling, it has to be, or in other words, it must be complemented with real world validation, iterative testing, and robust implementation and robust implementation practices.